Today we got this definite integral 0 to half pi log of 1 plus a times cos x over 1 minus a times cos x dx, and cos x at the bottom here. We require a absolute value to be less than 1. So if I just let this equal to a function in terms of a, because once a changes, the whole value of this definite integral may change or not. So once I do that, I can simply differentiate with respect to a. In other words, first we differentiate inside, treating a as a variable, treating x as a constant. Then we do the integration. And I'll explain the justification later. So here we have 0 to half pi log. Once we treat a as a variable, we immediately take this as a constant. Take this out. And when you differentiate log, first we use the reciprocal. 1 plus a cos x, 1 minus a cos x. Then we differentiate the inside. But the inside here we have a division. So we have the formula. We first copy it down the bottom. We square it. And we differentiate the top. Remember, a is a variable. Right? So we have cos x. Copy the bottom. Minus. Keep the top. Differentiate the bottom. Negative cos x. We have plus dx. Now we can simplify. Cos x, cos x, cos x. And 1 minus a cos x. So we only have one of them. This time, here, negative, positive. So we have 1 plus 1. So we take out the 2. 2 times 0 to half pi. Dx 1 minus a square cos square. So this time I say let's divide both the top and bottom by cos square. Right, because 1 over cos square and 1 over cos square minus a square. Because this time we notice that 1 over cos square x dx is exactly d tangent x. Because the derivative of, because we can tangent x equal to t. Remember, derivative of tangent x happens to be 1 over cos square x. Right, so in other words, dt is 1 over cos square x dx. And not only that, once we have this, I say 1 plus t squared, right? That's 1 plus tangent square. We have the formula 1 over cos square x. Okay. So here I can just replace and since we use substitution, I say here we have x, where x equal to 0, t should equal to 0 as well. When x is equal to half pi, t should equal to positive infinity. And we have, like I said, top now becomes dt. Bottom, we have what this term becomes 1 plus t squared. We also have minus a squared. Right. This time we simply factor out this one. And notice that a does not equal to positive 1 or negative 1. Right, that's my restriction. So this safe. And 0 to positive infinity, we have 1 plus 1 over 1 minus a squared t squared. And that is simply, if you put a square root here, put a bracket here, still the same thing, right? Square. Now, that becomes, right, this simply, right, treated as a entity, arctangent of, right, we may or may not use a substitution, but that won't be necessary because we are familiar with. So simply arctangent, right, this inside, then multiply by its reciprocal. Right? Reciprocal is just square root 1 minus a squared. Inside here we have this t from 0 to positive infinity. Right, once we have this, 2 over square root of 1 minus a squared. So positive infinity arctangent positive infinity half pi arctangent 0 times half pi. So this 2 is gone. So far, by letting our desired integral equal to a function in terms of a, we successfully worked out its derivative in terms of a, right, with respect to a. Right, so this looks like we can also say that derivative in terms of t is the same idea, right, 1 minus t squared. Right, so this looks like, right, so this looks like IA, right? So I of A minus I of 0. It looks like definite integral. Right? I of 0 equal to what? A equal to 0. Log 1, 0, 0. Right? Still I of A. So this, right, this can be written into a definite integral, 0 to a, I prime of t dt. Right, that is 0 to a, right, this one, square root 1 minus t squared dt. That is pi times arc sine t from 0 to a. That is just pi arc sine a. Now we've worked out the value for this definite integral. Okay, pi arc sine of a, right, as we just shown. Now here's the justification, like I mentioned before, for us to differentiate with respect to a inside here, then we integrate it. So the reason we can do that is because here we have a theorem in calculus. You can find that in any standard calculus books, which says, I'm not going to prove it here, but I've done a video previously. So the theorem says, as long as we have this inside function here, so 2 variable functions, let's call it f, 2 variables. As long as cosine, it says, as long as this 2 variable function is continuous everywhere in this domain, in this rectangular domain, x, 0, and not including half pi, because when you have cos half pi, you have 0 down the bottom. Right? We don't have a definition, right, for this function. But at least in this rectangular domain, right, the function is obviously continuous. So the question is that, is it also continuous at when x equal to half pi? Right? A is in between this, right? Any value in between this open interval. Right, let's say just limits. Because once we can show that, we can say that, okay, we can interchange. So once we let the limit, we let a approach a naught. A naught is, of course, any value in between -1 and 1. And we also let x approach half pi from the left-hand side. All right, so let's see. All right. Should be log. Minus a log. All right, so what's the limit here? Right, we have two variables, right? Not just one, two. So here we notice that when a approaches a naught, doesn't matter, that's okay. But x approaches half pi from left-hand side. So cosine approaches 0. Right? Doesn't matter what a value is. So you have 0, 0, 1, 1 over 1, log 1. Right? Right? Approach log 1. But at what speed? Right? So to answer this, we have we simply just rewrite inside here. Remember, if I just minus a cos x, then plus a cos x. Right? Minus plus. Then I can have I can have 1 plus twice of this. Right? Still the same thing. Right? If you plus this one to this one, still the same thing. Right? Except this part will approach 0. Right? Cos x approaches 0. So you have 1 plus 0. So notice this, we can immediately replace this with just this part. Right? Right? Just standard substitution. As long as it's right, multiplication or division, it's fine. We can substitute, right? Infinitesimal substitution. Right? Equivalent infinitesimal. Now here, cos x, right? No longer a problem. Right? Once we let this a approach a naught, x approach, so we have 1 at the bottom, 2a naught. 2a naught. It doesn't matter what a naught is in between -1 and 1. So it looks like the limit does exist. Right? All you have to do is to let g of a new function, I let it equal to f of a x if a is between 1 and -1, x is in between 0 and half pi, not equal to half pi. And if x equal to half pi, right, a is in between, you let it equal to 2a. Right. So that way our new function is continuous everywhere over this rectangle. Over this including both edges. Right? It's closed rectangular domain. Right? It's continuous everywhere. Right? So we can do the same thing to g of ax. Right? But it won't impact the integration value because we only change the functional value at just one point. And also we check the if dA f ax. So we check if this function, two-variable function, is also continuous, right? I'm not going to get into details, but it turns out, right, this function, by using this new function, you can also prove that it's continuous over this domain. Right? Therefore, we can interchange.